Hi everyone, welcome back to Automata, Grammars, and Computability. In this particular video, we will be talking about non-context-free languages. And basically what that means is we're going to talk about the pumping lemma for context-free languages, which is in CFL section 2.3. We'll explain how to use it to prove that a language is not context-free, and we'll start talking about what non-context-free languages are. This also gives us a chance to start talking about what Turing machines are just a little bit in this video. So the reason that we need the pumping lemma for context-free languages is there are languages that are not context-free. So for example, A to the N, B to the N, C to the N is not context-free. You can't construct a pushdown automata for it, but you can prove that it's not a context-free language using this pumping lemma that I'll talk about in a minute. So one thing I want to point out here is that the purpose of the pumping lemma for context-free languages is to prove that a language is not context-free. It doesn't tell you whether it's context-sensitive or recursively enumerable, which are the ones that are on the outside. It could be either of those. We don't know yet. So the pumping lemma is always used to prove that a language is not in a particular set. That was also true for the pumping lemma for regular languages. To prove that a language is in a set, you need to construct the automata for it. So if you wanted to prove that a language was regular, let's look at the bottom of the Chomsky hierarchy, that goes with a finite automata. So if you can draw a finite automata, then congratulations, that language is regular. Moving up a little bit in the Chomsky hierarchy, if you want to prove that a language is context-free, then you need to construct a pushdown automata. And next up, a language is context sensitive if you can construct a linear bounded automata, and a language is recursively enumerable if you can construct a Turing machine. And pumping lemma basically does the opposite in that it proves that a language is not in a set. Now, the intuition behind the pumping lemma is that the stack only stores one piece of information. For example, the number of zeros in 0 to the n, 1 to the n. And if you remember constructing the pushdown automata for this, we basically pushed a bunch of things onto the stack, and then we popped all of them off, and then we ensured that that stack was empty, and that told us, hey, the number of zeros and the number of ones is equal in this case. The language that I showed on the previous slide where you had three things, A to the N, B to the N, C to the N, you could count two of those things, like A and B, and make sure that they were equal, but that destroys the stack. And so having three things there, it's already not context-free. Another example that we had is the even palindromes, where you can save which element it is, and then you can check, hey, am I popping the same thing that I pushed earlier, and am I reading the right thing? So the goal of this slide is just to say, hey, to use the information on the stack, we pop symbols off, which destroys the stack as we use it, which means we can only count basically one kind of pair of things. Now, let's think about a little bit more with a pushdown automata for A to the N, B to the N, C to the N, which can't exist. I already told you we can only use a stack to store one piece of information, and we lose the information in the stack as we use it. And A to the N, we maybe push all those A's onto the stack and then pop all of them off to check that the number of B's is equal. And it basically makes us forget N. So that language was not context-free, but I didn't actually give you a proof. I just said intuitively why it shouldn't be possible to create a pushdown automata for it. So let's actually look at the theorem for the pumping lemma for context-free languages. And this should look familiar from what we understood from the pumping lemma for regular languages. If A is a context-free language, then there is a number P, which is the pumping length, such that for any string S in A, where the length of S is greater than or equal to P, S can be divided into 5 pieces. S is equal to U, V, X, Y, Z, such that the following conditions hold true. 1. U, V to the I, X, Y to the I, Z is in A for each I greater than or equal to 0. The length of Vy is greater than 0, and the length of Vxy is less than or equal to P. And this looks reminiscent of the pumping lemma for regular languages. That point about being able to count kind of two things at once appears here with that V to the I, Y to the I. So so that means that we're pumping two parts of the string together. You have a double pump. And the second condition, Vy, length being greater than 0, not both substrings can be empty. And there is a prefix that could appear in the string. It does have a length restriction, though. That would be kind of like that first part before you get into the part that's going to get repeated. Here, I want to talk about some common errors that I've seen people tend to make when trying to use the pumping lemma. These things already appeared when people were doing proofs for pumping lemma for regular languages, and similar things are likely going to stay true unless you take a moment to stop and think about it when you move on to pumping lemma for context-free languages. One common error is that people choose U, V, X, Y, and Z to be specific rather than a generalizable answer. So now we have U and V. For pumping lemma for regular languages, we had X, Y, Z. You could not pick the exact X, Y, and Z. You had the restriction of the conditions, which meant that you had to pick what I call an admissible X, Y, Z, and it restricts the space that you're looking at, but it doesn't tell you exactly what string X, Y, and Z could be. Another thing, and this tends to happen with proofs in general, is just lacking justification as to why a condition failed. So the one example I like is a to the n squared, and maybe you did the pumping lemma on that and you said, hey, I ended up with something that wasn't a perfect square, but you didn't discuss the bounds correctly. That's going to appear again here with pumping lemma for context-free languages. Basically, I want to make sure that you're doing your algebra. And I would say that CIPSR does not have sufficient detail on this to actually show those algebraic steps and show why this new string that I got is really not in the language. Requires some careful steps, at least in this class. So moving back to the pumping lemma for context-free languages, as I mentioned before, a context-free language can contain strings in which two separate parts are generated together. So let's look at this old example, 0 to the n, 1 to the n. The other example, which is even palindromes. And these languages we already know are context-free. So you can always pump basically the zeros and the the zeros and the ones together, or like the first part of W and WR together. And hopefully that intuitively makes sense as to why those strings will remain in the language even after you pump them. Oh, here's another example. It's even with we talked about even palindromes. It's also going to work with odd palindromes, and you can kind of see here, like we have X in the center that actually matches the X that is in the pumping lemma. So good. These are all context-free languages. Here's another one. Now, hopefully, while these are like appearing on the screen, you're starting to see what that pattern is that kind of tells you why these languages are context-free, at least intuitively. So another way to think about it, if the set builder notation doesn't kind of make that clear to you, and also this is how the proof for the context for the pumping lemma for context-free languages goes, is we use parse trees. And as you know, context-free languages are languages that can be generated with a context-free grammar. And so a parse tree kind of shows you how those strings are being generated. In the image, I have T, which would be kind of like the start, and then it goes into R, and then you can break that thing at the bottom of the tree up into U, V, X, Y, Z. And with a long enough string, some variable is going to have to repeat. With these infinite languages and only like a finite number of grammatical rules, you know that one of these variables is going to have to repeat. Now, a string in the language that is long enough has a tall parse tree, and some non-terminal has to repeat. And this tree structure is where you see the left and right UV and YZ, or U and Z, and you have to look at the parts that are going to get repeated in sync with each other. So hopefully the image makes that a little bit apparent here. T goes to R, and then you have X in the center, and then U and Z on either side. And then we have to think about V repeating and Y repeating. Okay. R is the non-terminal that is getting repeated here. And we can still basically apply those rules that are in R. Or you can omit R from the original parse tree because you can pump 0 times. So let's take a look at that language that we like, which is 0 to the n, 1 to the n, and look at it in terms of a grammar. Only the non-terminal S repeats. So the parse tree will look like the examples that we had, and you can generate many strings in this language by repeating S as many times as you want. So S is kind of like that part that's in the center that kind of gets pumped on either side. So good, we can see these parse trees. And we can see how S is the non-terminal that's getting repeated, and you can basically remove it. You can see what's left over. As a result, you can use S again and keep building that parse tree. Okay, so one thing to say is that kind of shows you how that tree is being built. But of course, we want to use the pumping lemma to prove languages are not context-free. So let's look at our new canonical example, which is A to the n, B to the n, C to the n. Another example is A to the n is a prime number. Turns out all unary languages are context-free if and only if they are regular. Okay, so good. Let's go ahead and look at this proof real quick for A to the n, B to the n, C to the n. This looks a little bit familiar to what we've done before. Assume that L is a CFL, right? So we start with that proof by contradiction. Then it means that the PL for CFLs, the pumping lemma for context-free languages, is true for L. That means there exists a value P such that for all strings of length P or more, all three of the PL conditions hold true. Then you're going to pick a string. In this case, we want to pick something that's longer than the pumping length. And usually when you have it in set builder notation, it almost always makes sense to replace some of those length variables with P, the pumping length. So I have A to the P, C to the, A to the P, B to the P, C to the P. And this is in the language by definition, and I know it's longer than P. And now, using the pumping lemma condition, Vxy is at most P symbols long. And now you have to think about the cases of what V, X, and Y can be. VXY is all A's and B's, or all B's, or B's and C's, or all C's. Okay, so now if we look at those cases, we can kind of see what VXY has to be. V and Y could each contain only A's or only B's or only C's, or not. One of them can contain a mix of symbols. For example, V could be all A's and Y could be all B's. So notice here, like, I don't really know what V, X, and Y are. I do have a sense of like what they could be, and I can restrict it to these cases, but I don't actually get to pick U, V, X, Y, or Z. I only am trying to meet those three conditions in the pumping lemma. Okay, so let's go by cases. Case 1, V and Y contain only A's. So by condition 2, one of V or Y must be non-empty. Pumping V and Y will increase the number of A's, but not the number of B's and not the number of C's, so you know that string is not an L. You can use that same argument for the B's and C's, so good. Case 2, which is the or not case, V or Y contains a mix of A's and B's. Pumping V and Y will create a substring that looks like this, A to the I, B to the J, A to the I, B to the J, which is a mix of A's and B's in order, and that is also a string that is not in L. And that same argument is going to apply to a mix of B's and C's. So really you have 4 cases, but you can see how case 1, that sort of covers 2 cases, and case 2 sort of covers 2 cases there. Now, you kind of just need to conclude your proof. The pumping lemma conditions cannot hold for this particular string that we got to pick, but the pumping lemma says that its conditions hold true for all such strings in L. So it must be the case that L is not a CFL. That's it. That's your proof by contradiction. And I hope by walking through this, you can see where these limitations of like what U, V, X, Y, and Z are, how I use those in this proof, and how I gave enough details, including a little thought, like the speech bubble that came out, which you would probably not write like that when writing homework, but that gives you a sense of like how much detail we actually want to see in these pumping lemma proofs. All right. So let's end the recording here. Thank you for watching.